were working on cutting things up into itty bitty, teeny tiny pieces so that we can find what the volume the piece generated, so that we can add all those volumes together to get what the volume of the solid was. Remember doing that?
Yeah.
This very well. Kind of annoying. Kind of annoying. Do you want to start from there, or do you have questions for me? Need me to back up in any way, shape, or form?
We're doing revolution check now, right?
We are.
Can I ask one about the homework?
You may.
Signed area.
Signed area. I
What
can
is
do
signed
that.
area?
What is signed area? Some parts of the graph are above the x-axis and some parts are below.
What about on a square root function? So it's like the square root of 4 minus x squared.
That's the function?
Yes, ma'am. It's the integral of that, sorry.
And we're gonna find the area
Yes.
between, oh, I see.
Yeah,
The instructions are find this integral from somewhere to somewhere. 2 to -2?
yeah.
But one thing you have to notice is you don't know how to find the antiderivative of the square root of 4 minus x squared. It's a quantity to a power, right? So typically we find the integral of a quantity to a power with a u du substitution. If you attempt that here, u would be 4 minus x squared. What would the du look like?
Negative 2x dx.
Negative 2x dx. So you would need at least an x out here, and you don't have it. So note that you cannot compute the antiderivative of that 4 minus x squared using our u du substitution. So I don't have something to plug the 2 and the -2 in. And what the hint is think geometrically. Instead of working toward this antiderivative, which we'll be able to find in chapter 7 with some fancier substitution, instead of thinking about it in that way, this looks like it's written backwards.
I think there's a setting somewhere in the camera.
Why did somebody do that to me? Now, where do I find that?
Is there, I forgot what the settings are.
I did too. Here we go. Better. Although it would be kind of fun just to do calculus with a mirror, right?
You have to watch the
Have to-
screen here.
Yeah, you just hold it near.
It's always something. Okay, so we can't do this with a u du substitution. So let's think geometrically. Does anybody know how to graph that?
Semicircle.
It is a semicircle. This is a y. And that is 4 minus x squared, and I square both sides. I can rearrange this equation to say x squared plus y squared is 4. You recognize that as the equation of a circle centered at the origin of radius 2.
Yeah.
But when I go from here to here, I've cut off half of the circle, right? If I took that, solved it for y squared, and then took the positive square root, I'm throwing away all the negative y values that are on that circle. So these are now gone. Kind of gone, they just went there. And now you're asked to find the area under that curve from -2 to 2. And fortunately, it's a circle. We can find the area of any circle. pi r squared. So half of the circle, 1/2 pi r squared. What's r? We have 1/2 pi times 2 squared, and there's our area. 2 pi square units of area. Okay.
Can we go over one more?
Mhm.
So it's the integral of the absolute value of 3x minus 2 from 0 to 9.
Right. Right triangle.
Well, it's, again, you can't just find the antiderivative in here. You can't just go and put the antiderivative in absolute value bars and say that that's the antiderivative. Because an absolute value function in general looks like what? A V, right? So it doesn't, it kind of has a sharp corner, right? So it doesn't have a single function that gives me both pieces of that graph. It's a piecewise defined function. So we could find that piecewise defined function, or we could draw a picture. We've got a V-shaped graph, and we want the area under the V-shaped graph from 0 to 9. So typically this would look like the line y is equal to 3x minus 2. So here's minus 2, slope of 3, and it's going to cross the x-axis somewhere. That's where the vertex of the V is. What value of x makes the stuff inside that absolute value sign equal to 0?
2/3.
Okay, so when x is 2/3, I got the end of the V. When x is 0, y is 2,
Why is -2, right?
but it's an absolute value bars. And when x is 9, what's the y value going to be? 3 times 9 is 27, minus 2 is 25. So I'm just going to put it right here. And so the graph that we're talking about in that interval looks like this. And we want to find the area from x is 0 to x is 9 above the x-axis. That's what that integral is telling me. So again, if I don't want to find the equation of this line and that line, I can just see in my picture, I've got 2 right triangles. And I can add up the areas of each of those right triangles by taking 1/2 of base times height. Okay, the fact that they're right triangles means, well, this one has a base of 2/3 and a height of 2. So the area right here is 1/2 base times height. Let's work on this. Okay, I'll help you. The height is 25. How wide is it down here?
8 1/3.
8 1/3? Because all the way out here takes me to 9, here takes me to 2/3. So that's 8 1/3, 24, 25 thirds. So now I'm going to add to that 1/2 base times height. So I have 4/6 plus 6, 25/6. So the total area is 629/6. Did I put one of those on your Cal 1 final list semester? I think I did, not one that messy. So both of those have the same theme, that even if you can't find the antiderivative, if you're describing a physical entity like area, if you know what the picture is, maybe you can just go back to the good old geometry, find the area that way. Anything else? Okay, so let's rub that off and recap what we did last time. In the first part of the class, we were finding a volume of a solid that's description was given to us. Here you have a solid, its base is sitting on the XY plane with the property that if you make slices in that solid perpendicular to the x-axis, each slice looks like this. Circle, semicircle, square, isosceles triangles, looks like something that you're described. So if you're told something like that, so in 6.2, so a recap. The first part, we are finding the volume. Got some more juice in it. Find the volume. Well, that's not that great either. The solid whose base is in XY plane and cross sections of this solid are all similar shapes. We made the cross sections perpendicular to the x-axis, but there's nothing magical about doing things perpendicular to the x-axis. We can do it perpendicular to the y-axis if so described. But if our cross sections are perpendicular to the x-axis, then we've got some sort of region in the XY plane. Maybe it looks like that. Solid is coming out of the board like that. Our cut looks like an infinitely thin rectangle of width delta x. And it generates some side that's going to be in the description. If the description says that all of our cuts look like squares, then I know how to find the volume of that slice. Side squared times the thickness. I add up all those slices with a Riemann sum, let the number of slices go to infinity, and I have a definite integral. If the slice is whatever area, I take the area of the slice, multiply it with its thickness, the Riemann sum becomes a definite integral. So this is going to be described. It might be a square, in which case the area function is side squared. It might be a circle or a semicircle. It's an entire circle. It's pi times the radius squared, where the radius is going to be probably half the length of the side, right? There's a semicircle coming up here, and S represents the diameter. If you're told you've got an equilateral triangle, we determined that the area of an equilateral triangle as a function of a side was square root of 3 over 4 times side squared.
Here, I should know that.
Okay, so let's find one of those and do one of those. Uh-oh, signed out. Why have I been signed out? It says it's still recording. So maybe it signed me out whenever I didn't sign out before. I've been on Zoom today, so why would it say that? That's probably something going on in that cloud.
Small.
Exporting the zoom to the wall space already.
The Zoom god in the cloud says, no, I am logging you off. Okay. So the region in the XY plane is the circle x squared plus y squared is equal to 4. So a solid has as its base of the solid in the XY plane is the circle x squared plus y squared is 4. Slices of this solid perpendicular to the x-axis are all, does it matter to you which one we do?
No.
Okay, so let's say they're all equilateral triangles. Find the volume of this solid. I'm not real good at drawing in 3 dimensions. But visualize something that if you looked at it from the bottom, you see a circle. But if you look at it from the top, you see a bunch of equilateral triangles butted up together. Who can draw in 3 dimensions?
I can try.
Try. Let me see, and then you want to come up and try, or you want to try
I'll come up and
privately
try.
first?
Down there.
Not that the 3 dimensions matters, but I just want to see if you have hidden talents. Can anybody sing while she does this?
Yes, I'm known for my singing abilities.
Hey, what about cook? I'm hungry. Can anybody cook while she does this?
That's Travis.
Yeah, I got that.
There you go.
Kind of comes down, not really sure how to show that.
Except for be kind of sharp on top and not rounded, right?
I think so.
Because you're going to get smaller and smaller equilateral triangles as we move toward the end of the diameter.
Yeah, it's an odd shape.
It's an odd shape. Very
Okay.
good. I like that.
Thank you.
That's very good. Here's the best I can do.
Yeah.
And then I'm gonna put my slice in there. Where'd my red marker go? Gosh, I thought the guy in the cloud come took my red marker. I can make a slice now. I can call that delta X and that S. Then I can pull my slice out and show it to you. I don't know if that's legal, but I just did it. And there it is. And so I know what my plan is. My plan is to set up the definite integral, put the area of the slice in here, and then integrate it as a function of X, not as a function of S. As a function of S, I'm integrating square root of 3/4 S squared. So my plan, back. Volume is to integrate the square root of 3/4 S squared as a function of X. So that's my next task. It depends on where I put that rectangle. It gets shorter and shorter based upon top graph minus bottom graph, right? Can you tell me the equation of the top part of this circle?
It's the square root of 4 minus x squared.
And what is the equation of the bottom?
Negative.
Negative square root of 4 minus x squared. So S is top minus bottom. Top minus a minus is going to give me 2 of those. You find where we got the square root of 4 minus x squared? Right, so top minus bottom tells me that that S has length of 2 times the square root of 4 minus x squared. So we put that in where the S is and then integrate. We're going to integrate over the range of the x's, so it's from -2 to 2. Then we have the square root of 3 over 4. Then in here, side squared is 2 square root of 4 minus x squared. Then we square it because of the area formula. Then we make it volume by multiplying by thickness. Quit writing that file over. Ooh, I went the wrong way. Go back. Wow. There it is. Are you convinced you could finish it from here?
No.
You square the 2 and get 4, cancels that 4, pull the square root of 3 out front. That took care of this number, that number. Right? Then you square this and you just get 4 minus x squared. And then if you can't do that one, I'm going to kick you out of the class. I'll stop right there. Okay? That's the idea of the first part of the class. So recap continues. In the second part of the class, we were generating our own solids by taking a 2-dimensional region and revolving it around an axis. You take a 2-dimensional region and revolve it, has to be around an axis, or revolve it around either a horizontal line or a vertical line. You take a 2-dimensional region and revolve it around a horizontal line, you generate a 3-dimensional solid. We want to find its volume. What we did last time is we found its volume by slicing that region with rectangles perpendicular to the axis of revolution. Then I'm going to do parallel to the axis of revolution. So the second part was generate a solid by revolving a region R in the XY plane about a horizontal or vertical line, right? The axis or the line of revolution. So for instance, if this is my region R, and maybe I want to revolve it, say, about the x-axis. Then if we partition the region with rectangles that are perpendicular to the axis of revolution, a known shape is generated by the partitioning element. My axis of revolution in my general example here is the x-axis. So my partitioning elements have width of delta x. if I revolve this particular red rectangle around the x-axis, coming out of the board and going back in, it generates something that looks like that. Right? What did we call that? Generated a washer. If my region is butted up against the axis of revolution, we technically have a washer, but one without a hole. So we just called it a disc. And the plan was find the volume of that one washer or one disc, and then add them up with a Riemann sum and get a definite interval. If we get a washer, we know the volume of a washer is going to be the area of the face times the thickness. So in my picture, the area of the face will be a pi r squared, or if I need to subtract off the whole, then the thickness is going to be a dx. And so we would get that our volume was pi. To get the big circle, we'd go find what r squared is. To make a hole, we subtract off the radius of the hole. And then the thickness is going to be whatever, dx or dy, depending on which way we're revolving. So d whatever, which I'll just call thickness. That becomes a Riemann sum, make an infinite number of them, and we have that. Where the outer radius would take us from the axis of revolution to the part that generates the top of the disk. The inner radius goes from the axis of revolution to the inner. So capital R means outer radius, measured from the axis of revolution. Little r means inner radius. All right, I think we had a handout of problems.
What would you do if the graph was on both sides of the axis that you rotated?
Still generates a solid.
So you just
If it's on both, it'll
figure out
like
like taller.
fill in itself if it's symmetrical.
What do you mean taller? I would just do the same thing. I'd slice up the region with rectangles.
Like
I
if you
think
were,
they're saying like, what if it crosses the x-axis? What if the shape
So,
crosses the
and then you have like a
x-axis?
point right there, and then you partition it
Mhm.
and you rotate it around this axis. Like this is taller on average, but it has like a piece that's
I just look at infinite number of slices. It would be given by the function. Right? There'd be some sort of function that described that little nose right there. Just do the
It
same
would even
thing.
itself out.
it would work itself out.
Mhm.
Okay.
Mhm. Not a problem. It is not a problem. Let me see where my handout of problems were. Not there. Not there. What did I do with them? There? It looks something like that? Do we have something, remember the problem that I emailed you long time ago? I think one of the examples is, let me see, do you have it so that I know what it looks like? Maybe it's this thing here. It is that thing in there. Okay, so my first example was, oh, I just licked ink off my finger. The square root of the sine of x. How about that? Did we do that one yet?
We have not.
All right, so we're going to draw the graph of f of x is equal to the square root of the sine of x. And underneath that graph between x is 0 and pi, and above the x-axis, we get a region. We're going to take that region and we're going to revolve it about the x-axis and find its volume. Well, we're gonna revolve f of x is the square root of the sine of x for x between 0 and pi about the x-axis. Okay, so we will revolve that, and I'm going to consider the region between that graph and the x-axis. So I'm leaving out a lot of the words. Do you know what the sine of x looks like between 0 and pi? So the square root is just going to make those numbers, smaller. So it looks like the graph of y is the sine of x after you take the square root of them. So between 0 and pi, it probably looks something like that. The highest peak is going to be the square root of 1, which is still 1. Right, so I'm going to take that region, revolve it about the x-axis, and we make some sort of chubby looking football. Right? And we're going to find the volume. So our region, it has as its bounds the axis of revolution. That means we're not going to get any holes in it when we take our region, partition it with rectangles. So we're going to get not washers, we're going to get discs. Agreed? We'll get a disc that has that as its radius. So we just need an integral of a pi r squared times our thickness of dx. So we get a disc pi r squared times dx as our integral, where that's going to be the radius because this thing's going around. So what am I going to use as my radius?
The square root of sine of
Square root of
x.
sine of x. I'm going to integrate. It'll be from 0 to pi times r, which is the square root of the sine of x, squared times the thickness, dx. Well, this one looks pretty easy to finish. We square that and we get rid of the square root sign. Pull the pi out front. We're just integrating a sine. What do you get when you integrate sine? Cosine. You get a positive cosine or a negative cosine?
Negative.
You do get a negative cosine. What is the cosine of pi?
1.
Other one? Cosine of pi is -1. So you get minus 1. And then cosine of 0
Is 1.
is 1. So I have minus a minus gives me that. So we have exactly 2 pi cubic units of volume. Any questions on that one? These videos come out clearer than it looks. Okay, let's do the next one. Maybe the next one might have a washer. The next one, we've got the line y is equal to 1/2 x. So that's the line through the origin.
Or sorry, the number.
Oh, okay. Well, number 2, we're going to go back to the y-axis. So we have y is equal to 1/2 x, the y-axis, and the line y is equal to 3, and we're going to revolve it about the y-axis. Put it here, no, put it there. I'm gonna put it right here. I'm gonna erase this guy. we're going to revolve f of x is equal to a half x y-axis, and the line y is equal to 3. So region R is bounded by those 3 graphs. Revolve R about the y-axis. And find the volume of the solid that's generated by doing that. So the picture looks like y is equal to half x is pretty wide out here. Y-axis, and then let's put the line y is equal to 3 here. So this triangular region, we're revolving that about the y-axis. So what's that going to generate if you take a triangle and revolve it about the y-axis? Cone. You don't need any calculus. I can find the volume of a cone.
1/3 base times height.
1/3 area of the base times height. Okay, so let's do that. Let's find the volume of this using geometry. This will give us a cone whose volume is 1/3 area of the base times the height. Okay, so this is by geometry. And you look at the picture and tell me what the radius of the base is going to be.
3, 6.
6, right? When y is 3, here, this x coordinate is going to be out at 6. So this is going to generate the radius of the base. What's going to be the height of this cone? 3. So we get with geometry, 1/3 area of the base would be pi r squared times the height, which is 3. 3's cancel, we get 36 pi cubic units of volume. So that's just going to be there to reaffirm that our calculus is going to work. Because now we're going to do it by slicing this region up with rectangles perpendicular to the axis of revolution. So this time I'm going to slice it up with little dy rectangles. Like this. Oh, red, don't leave me out. Maybe you can see that. Take that little red rectangle and swing it about the y-axis. And what shape do you get? You get a circular disc, right? So pi r squared times the thickness, but this time the thickness is dy. And my r is going to be right graph minus left graph as a function of y. So what am I going to use as r?
2y.
R is going to be 2y. Okay, so this is going to give me a disk. Pi r squared times dy is going to go in my integral sign over the range of y. So what numbers goes on my integral sign?
0 to 3.
0 to 3, very good. We're going to integrate from 0 to 3 pi, we said the radius was 2y squared dy. We're going to finish this because we're going to get 36 pi out of this. So we square that and we get 4y squared. Let's take the 4 and the pi out front. So we'll have 4 pi times the integral of y squared. You said 0 to 3. And so we have to evaluate the antiderivative. 0 to 3. 0 is going to give us 0. 3 will give us 27/3, which is 9. My gosh, by golly. Calculus does agree with geometry. What about that? Does that give you the thrill that it gives me?
Yes.
Yes.
All right, what's next? You ready for next? Okay. You say they're going to make washers. So what I want you to do is draw me the region between the two graphs of y is equal to the square root of x and y is equal to x squared. We're going to take that region and revolve it about the x-axis. Y is equal to the square root of x and y is equal to x squared bounds a region. And we're going to go take that region and swing it about the x-axis. Picture's going to tell us everything. All right, y is equal to x squared is that. We only need to worry about this first quadrant, so let's put our parabola like that. Oops, I just wrote the wrong one. So we got this little cigar-shaped region here, and we're going to swing it about the x-axis. So it makes some funny looking bowl that has concave down insides, right? I don't care what the three-dimensional shape looks like. I just want to watch my rectangle go around the x-axis. So the plan here early on is all of our partitions are perpendicular to the axis we're going around. That's why I drew it that way. When that goes around, it's going to leave this hole here. That's going to trace back down to here. And we've got us a washer. So we take big disk minus the little disk to give us the overall volume. And so what I've been writing is our volume is going to be pi outer radius squared minus inner radius squared. I guess I should even factor out the pi, huh? Times the thickness of the rectangle. And as an integral. My rectangles are vertical, so my thickness is a dx. All of this stuff in here are going to be functions of x. The outer radius is going to be whatever takes me to the top of the rectangle to the axis of revolution. So how long is that going to be? Square root of x. The inner radius takes me to the lower graph, which is the x squared. So this is the outer radius. This is the inner radius. They're already written as functions of x. What I probably need next are the numbers that go on the integral sign, the range of the x's through the points of intersection. So I'll find this point of intersection here, and you're going to tell me where the two graphs intersect.
0 and 1.
Okay. The only number whose square is the same as its square root is 1. When x is 1, so is y. So the numbers on the integral sign go from this 0 to that 1. So here we go. Volume is equal to the integral from 0 to 1 of pi. You said the outer radius was the square root function, and I believe you. Squared minus the inner radius squared times the thickness. We're going to get the number out of this because later on, we're going to partition the region with rectangles parallel to the axis of revolution and find the volume of the exact same solid using a different technique. So let's go and finish this. When I do the squaring inside, I've got to integrate x minus x to the fourth. Pull the pi out front. So my antiderivative is x squared over 2 minus x to the fifth over 5. From 0 to 1, the zeros in each of there give me 0. 1/2 minus 1/5 is 5/10 minus 2/10 is 8/10.
3/10.
3/10. In my head, I saw a 3. So it's 3/10 pi cubic units. Okay.
That's just like basically one, right?
Basically, yeah, pretty darn close. Okay. Let's see, where am I now? Number 4. We're going to take the solid that is formed by revolving the region in the first quadrant, bounded by the graph of y is equal to x squared and y is equal to 4, about the line x is equal to 3. So draw me in the first quadrant, y is x squared and y is equal to 4, and it bounds off an area if you include the y-axis. Y is equal to x squared and y is equal to 4, quadrant 1. We're going to go about the line x is equal to 3. Quadrant 1, I don't need to draw anything over here. There's y is x squared. There's y is 4 in the first quadrant. Where does the line y is equal to x, where does the parabola y is equal to x squared intersect the line y is equal to 4? What's the ordered pair over there? 4? And so if that's 2, then let's put the line x is equal to 3 right here. That's the axis of revolution. We want to find the volume of that solid, so it's going to make some funky looking solid. You want to partition the region with rectangles perpendicular to the axis of revolution. So they've got to go dy style, right?
Wouldn't there be another R area, like another region, if the function kept going until it hit the 3 line?
It said just.
Say it again.
Like, okay, so the functions would obviously keep going.
Right, but it said just consider R to be the region between them,
Oh, okay.
right?
you
So
would-
I'm not going to do that and get a little triangular region. R is the region bounded in the first quadrant by the graphs of y is x squared and y is 4. Okay? So it's not going to be bounded by the axis of revolution, bounded by the 2 graphs. Good question. Okay, so I'm armed only with knowledge of partitioning things perpendicular to the axis of revolution. And so I've got to put my rectangles going this way. So that rectangle has a thickness of dy and has a length of right graph minus left graph, but who cares how long that is? Because as this goes around that axis, it's going to generate a big disk with a little disk missing inside. right? It's gonna come around here. This is floating off in space. It's supposed to be right here, but I didn't want to superimpose it on my graph. Right? If I do superimpose it on my graph, this rotates until it hits the board again. This makes the circle. It's gonna be the hole. And then that goes back into the board. Gravity keeps pulling my lids. But I get a big old washer. So I've got to take pi times the outer radius squared minus the inner radius squared times the thickness. And that's telling me everything has to be as functions of y. To figure out the outer radius, position yourself on the axis of revolution. And look how far back you have to go to hit the farthest endpoint of that rectangle. 3 units, right? You get to go all the way back. No, yes, 3 units, all the way back to here. That's gonna be 3 units no matter where I put the rectangle, right? Then how far do I have to go to get from here to here?
It would be 3 minus x squared.
It would be 3 minus x squared. Because here's y is equal to x squared, except, remember, we need everything as a blah, 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 y. Right? Because we're dy in it. Right? There you go. So here's big R. Big R goes this way. And little r goes that way. Okay, so big R is always 3. And little r is 3, take away whatever that particular length is. That length is x is square root of y. So 3 minus the square root of y. So the volume as our pi, big R squared, little r squared, times our thickness, in this case we said was dy. All right, now let's put all of the pertinent information in there. Big R is 3. Little r is 3 minus square root of y. Then we got to square it. What am I going to use for the range of the y values on the integral sign? Up the y-axis, I'm going 0, 4. Okay. All right, we're going to do this integral as well because in a few minutes we're going to find that same volume by partitioning parallel to the axis of revolution, and I want to show you to get the same number so that you can get through them again. So we got to square everything. Square the 3 to get 9. Be careful when you square 3 minus the square root of y. That means 3 minus square root of y times 3 minus square root of y. You're going to get a middle term. Yep. And 6 square root of y is the middle term, and your last term is plus y. You good with your algebra? So now I'm going to take the parentheses off, do the subtraction, and I lose the 9s. I'm going to write the square root of y as a y to the 1/2 so I can integrate it. We'll do it over here so I can see it. So I've got pi out here. 9 minus 9 is 0. 2 minuses gives me a 6y to the 1/2. And then minus y when I distribute that minus sign. 0 to 4. I'm going to add 1 to the power and divide by that new power. So 1 plus 1/2 will give me 3/2. And I'm going to divide by 3/2, so I flip it over and multiply by 2/3. What's 2/3 of 6? You get 4y to the 3/2. And this is y squared over 2, right? That's where the 4 comes from. Then we have to evaluate this from 0 to 4. Notice again that 0 is going to give me a bunch of zeros. Can you tell me what 4 to the 3/2 is? 8, because that's a square root of 4. Then we cube it. So that's going to be 2 cubed is 8. So this is 8 times 4 is 32. 4 squared is 16, divided by 2 is 8. 24.
Yeah.
And then I got a pi hanging around out here. 24 pi cubic units. Good. Okay, so if you partition a region with rectangles perpendicular to the axis of revolution, you will get a disk or a washer, depending on whether we have a gap. And our plan is pi r squared times the thickness, kind of thing. So time to go. Why are there people out there? You get out of here. Okay, good. They just know we're having fun in here and they're trying to listen for free. Okay, so now we're going to partition the region with rectangles parallel to the axis of revolution. Let me draw our regions here. Suppose I have a region in the XY plane. X is equal to A, X is equal to B, and our axis of revolution is going to be a horizontal line. Oops, I said, I can't do that one. Got to do this one, right? I want it parallel. I do that one. So it'll be a vertical line. Or the other case, if I wanted to go around a vertical line, then I'd have to have some version of this. Because here I can partition with rectangles that way. The other one I can partition with rectangles the other way. If I take this little black rectangle here, swing it around that axis there. I'll take that black rectangle and rotate it and bring it back. Ignore the rest of the blue. I'm just taking one slice all the way around and back. It's going to make a hollow can, right? It's going to make a hollow can. We're going to call that hollow can a shell. It's going to have a little thickness as its lip. In this case, the thickness is going to be a delta X. If I take this kind of region and go about a line that's horizontal, does the same thing. Take that thing around here. It'll end up down there. And it makes a can again. Right? We're going to call those cylindrical shells. So a series of cylindrical shells okay, so our plan here is partition region with rectangles parallel to the axis of revolution. And we'll use a shell method. Easy to remember. If partitions are parallel, you'll make a shell. Nothing rhymes with perpendicular. So we'll just say, and then the other one if you go perpendicular. Parallel makes a shell. So it doesn't necessarily mean dx dy. It means which way you partition, parallel or perpendicular. Parallel, you can use a method of shells. Perpendicular, you'll use the methods of discs or washers. So now we got to figure out what the volume of a particular shell is going to be. Well, it's hollow, so I can't use the volume of a can formula because that gives me everything inside. So what I'm going to do now is take the shell that's generated and cut it open and lay it flat. And what does it look like? Rectangular slab. I can find the volume of a rectangular slab. That length times thickness. Okay, well, that length I can figure out. That's going to be the height of the rectangle, right? Top graph minus bottom graph. Or if I have here, it's going to be right graph minus left graph. Okay, so let's draw that now. Right, take that one and let's cut it open. Here it is. And it's got its little thickness of D in this case, which is the D, dx. And this was H. And so now I need to figure out that dimension. I need to figure out how long it's going to be once I cut it open. It's going to be the circumference of the circular base. What's the formula for the circumference of a circle in terms of its radius? So this is going to be a 2 pi r. Same deal here. I'm going to generate an H and a 2 pi r, and then the thickness in this case would be a dy. So all of this all the way around here becomes a 2 pi r. So that's my plan. I take all of these little 2 pi r h times thicknesses for each little rectangle, make this little Riemann sum, let the number of rectangles go to infinity, and I get an integral that has basically that shape, 2 pi r h times thickness. So if we're going to do shells, we have volume is equal to 2 pi r h times the thickness, which is either a dx or a dy. And then our Riemann sum is going to give us that. Now, if you look at either picture, whether we have a dx integral or a dy integral, h is either top graph minus bottom graph or right graph minus left graph. Does everybody agree with that? Mm-hmm. R is as we figured before. It's going to be the distance from the axis of revolution to somewhere kind of in the middle of the rectangle. Doesn't matter because we're going to shrink the width of the rectangle down to 0 with our limit. But R is going to be the distance from the axis of revolution to the middle of the partitioning rectangle. So here I'm going there. So it does depend on where I'm placing it. If that's just the y-axis and that's just the x-axis, if I'm measuring the distance from a y-axis, then that's just going to be a variable, right? It depends on where my rectangle is in the region. It's going to be at the variable x in this region here, where x is a number between a and b. If I'm measuring my r this way, then it's a height. It's going to be some number y between c and d. So r might be x or y, or it might be a distance. It depends on whether I've got this at the x is 0, x is 0 or y is 0. I could move it somewhere else. Okay, but it's going to involve a variable. It depends on where the region is placed, or where the rectangle is placed. So let's go with a particular example. we are going to rework all of the examples we did earlier. So for my example number 4, it says go back to example number 2, which was that triangular region that made the cone for us. Well, y is equal to a half x, the y-axis, and the line y is equal to 3 revolved about the y-axis. We've got y is equal to a half x, y-axis, and y is equal to 3 as our region R. And we're going to go about the y-axis. So that picture. Let's see, y is equal to a half x, y is equal to 3. So at this point again was the ordered pair 6, 3. We're bounded by the y-axis and we're going about the y-axis. And that was the one that had the volume of what, 36 pi or something? So we're making the exact same cone. We're just going to approach finding its volume by making slices parallel instead of perpendicular. So if I slice it up parallel, I'm making dx's, right? An infinite number of rectangles where a typical one looks like this. So I've got a little dx action going on. That's going to come around here and make a stubby little cylindrical shell. Like that. So my plan is 2 pi r times my dx. H, 2 pi r h times my dx. Right, so here is h. R, I need black. This is going to be our R. And that's going to be our thickness. Volume 2 pi r h times the thickness. Thickness of the rectangle. So here our thickness is dx, so I need everything else in terms of x. What will you write as h?
I think it'll be 3 minus.
3 minus 1/2 x. Top graph minus bottom graph, just as we did when we were finding areas. So h is 3 minus 1/2 x. I'm going to take the 2 pi out in front of the integral sign. Now we got to figure out what r is. So when I place my rectangle here, r is that distance. Place it here, r is that distance. So it grows as I move along the x-axis. So in this case, r is just x, right? Some x value between 0 and 6. So I sum those up and I make a definite integral. Okay? All right, we're going to do this integral and we're going to get 36 pi again. So let's knock it out. Multiply that out and get 3x minus 1/2 x squared. And so its antiderivative is going to be 3x squared over 2 minus 1/6 x cubed. Then we have to evaluate that from 0 to 6. Arg. The big numbers. Let's see, 6 squared is 36. 36 divided by 2 is 18. 3 times 18 is 54. Six cubed divided by 6
6 squared, so 36.
is 36. Now, 54 minus 36, would that be 18? 2 pi times 18,
36.
same shape, so it should have the same volume. Just different ways of looking at it, with geometry, with discs, with shells. All right, so next, we still have time for a next, maybe we can set it up.
We have 7 minutes or
7
6 now.
6 minutes.
Rework example 3 using shells. That one might be boring. Let's make a jump to number 6. Let's rework example 4 using shells. Let's make the jump. So let's rework example 4 using shells. Example 4 had the region y is equal to x squared, y is equal to 4. In the first quadrant, about x is equal to 3. Okay, so we had parabola, line, y-axis. That's our region. This was the ordered pair 2, 4. And we're going to go about x is equal to 3. So when we partition this with rectangles parallel to the axis of revolution, are we going to get dx's or dy's?
Yes. Yes.
Yes, my line's this way, so my rectangles are going to be that way. So here's a typical rectangle. It is still a dx. So since it's a parallel, our plan again is 2 pi RH times dx. H is how tall that rectangle is. How tall is that rectangle?
4 is going to be 4 minus
X
squared.
4 minus x squared, top graph minus bottom graph. It depends on where I place it, right? Now we got to think about what R is.
It's gonna be X again, right?
Not quite, because I've got to measure from the axis of revolution. So I'm starting out 3 units away from the y-axis, and then wherever this is placed, I've got a smaller distance. From here to here, in the last example was x. So now this should be 3 minus x. That's going to be our R. Let's measure from the axis of revolution. And then the x's on the integral sign will have the numbers going from 0 to 2. So 2 pi RH dx. So here's the 2 pi. 0 to 2. R is 3 minus x. H is 4 minus x squared. And then a dx. And I bet we get the same answer that we got in example 4 because it's the same shape, just a different approach. What did we get in example 4?
24 pi.
It should equal 24 pi when you're done. And you'll just have to, I guess, do that on your own, because you're gonna have to multiply this out. You get 3 terms again, and then there's the numbers. And you do something, you do the same answer. Parallel gives you shells, 2 pi RH times thickness. Partition perpendicular gives you washers, pi times outer radius squared minus inner radius squared times thickness. If you're not consistently dx or dy, you gotta look at your picture to decide that. All right, you guys have a great weekend. That takes us to the end of section 6.2. I've got some homework problems for you. Open on the 30th, I'll go open it now.
Yeah, open here,
I have write-ups.